Okay, what we're moving on to is really what your calculator allows you to do. So the common log is basically a log that has a base of 10. Calculator is set up for common log, so when you press the log button on your calculator, that's what it means. When you see a log done out, basically they'll go, okay, what's the log of 1.2? If you see no base on it, you can assume that it's a base of 10. So to do this one, and they typically give you these, but you can just literally go log of 1.2, hit equals, and it's 0.07918.
Can I have a piece of paper?
Yeah, absolutely.
It seems like I always run out in this class.
Here's some notebook paper even.
I have a bunch at home,
Okay, so that literally, and there's two types of things here. There's something called a mantissa and a characteristic, but we're not going to get into that. I just want you to know how to do these on your calculator. Okay, so if it says, find, and literally you're just using your calculator, the log of 43. Okay, if I press into my calculator, log 43, it's going to give me 1.6335. Here's what that says. As crazy as what that sounds, 10 raised to the 1.6335 power is equal to 43. That is weird as what that sounds. Okay? So that's literally, when I do the log of 43, I'm going, what power would I have to raise 10 to get 43? So anytime you don't see a log there, a base on your log, understand that it's just a base of 10. Sometimes they give it to you backwards, okay, where they actually tell you what it's equal to, and you've got to figure out the anti-log. In other words, what you take the log of to get that. So they give you this side, and they don't give you this side. So it will literally say, use the scientific calculator to find the anti-log of 3.073. Now, again, all it is calculator use. The anti-log is the inverse of the log. So I go second, I hit the log button, and I go 3.073, and I hit enter, and it tells me, oops, I think I have an extra. I have 1,183. Now turn around and take the log of 1,183 and you get that. Okay, you're going back and forth here. So when I take the anti-log and it gives me this, what that means is if I took the log of 1,183, it would give me that. It's a circle, okay? Literally in this section, the only thing that they are asking you to do is to find the log of something on your calculator and the anti-log, which is just doing second, log, hit the number, and it tells you what you would have to take the log of to get that number, okay? This entire section, that's all it's doing. If it asks you for the mantissa and characteristic, don't worry about it, okay? All we need out of this section is to be able to do that kind of stuff, okay? Literally, that's all I'm going to ask you to do, okay? So that's what's called a common log. A common log has a base of 10. But we also want to talk about something called a natural log. A natural log has a base of e. Okay, now that sounds weird, but if you give me a second, we'll discuss it. Again, it's going to be mostly calculator use. What's the value of pi?
3.14.
3.14, and it continues on forever and ever. The value of e is like pi. It has a value of 2.718. Now that continues on forever and ever. If you'll look at your calculator, there is actually an e on your calculator right underneath where the pi is. Okay, did you find the pi on there? Look at right underneath where that is. Do you see the e? It's just like pi. It has a value, but it is understood in certain formulas. There's an e, just like in certain formulas there's a pi. If I asked you for what the circumference of a circle was, what would you tell me? You remember?
Pi
No.
Is it pi r squared?
No, that's the area of a circle. The
Oh.
circumference of the circle is 2 times pi times r. Pi has a value, okay? We know we can hit it in a calculator and it can give us the value. It's the same thing for e. There are certain formulas. There is something called a PERT formula, and it's used in finance, okay? And it allows you to get your accrued interest. That e is the e on the calculator, okay? This is a principal times the e raised to the rate times the time value. And we're actually going to do a couple of those, but the natural log has a base of e, okay? You have a natural log button on your calculator. It is right below your log button, and it literally looks like LN. When you see it in your book, it's weird. It looks like, in my opinion, it looks like IN. Okay, just the way that the printing in the book is. But be careful that if you see that, understand it's an L. I think it's like that. Okay, in the book, but it's an LN, it's just a lowercase l. I always do an uppercase L because to me, I don't like the fact that the L looks like the I, okay? So, if I were to ask you, using the calculator, to find the natural log of 3.925, that literally just means I'm taking my calculator, I'm hitting the natural log of 3.925, and I'm going to get 1.3674 when I round it off, just by calculator use, okay? Does that make sense? So you got to pay attention to whether they say the common log, which is the LOG button, or the natural log, which is the LN button. Logarithm's the same. What's different is this has a base of 10 and this has a base of e. So you go, okay, what does that even mean? Okay.
Is there a way to do these like longhand? Not that I want to know, but
They used to, believe it or not, they used to in the back of the book, the back of like a pre-cal book or an Algebra 2 book, they used to have tables of logarithms. And you would have to go back in the table and find the answer. As far as mathematically, no, there really isn't, okay? Maybe for somebody who's way more better at it than what I am. But there used to be common log tables. You'd never see a book like that anymore. Now, what if I have something like this? Now, this is where it gets weird, okay? And in your book, if you look at example number 2 on page 622. Oh, by the way, if you want to know what E is equal to, how they got the E equals 2.718, it literally was acquired like this, okay? E is equal to 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 3 plus 1 over 1 times 4, and they keep going on and on and on and on forever. That's where E comes from. Okay, you don't have to know that, but that's where they get that from. Okay, but let's look at example 2. Do you see where it says find x? Sure, okay. Find x if, and you see where I'm talking where it looks like IN?
What page are we on?
Page 622.
Oh, okay. Mm-hmm.
Okay, and it looks like IN. Does it not look like IN in your book? Okay, but it literally means LN. Okay, it's like a lowercase l. The ln of x is approximately 3.4825. Okay, so I'm trying to find x. Here is my problem right here. So what I'm saying is e to this power is equal to x, right? But there's an easy way to do it. I mean, I literally could take my calculator and go e raised to the 3.4825 power, okay? And I could get my answer. But if I have a logarithm on one side, this is a natural log, I can find my x by doing the inverse or the anti-natural logarithm. So I'm basically moving my natural log to the other side by, if you will, dividing. That's the same as taking the inverse of the natural log of 3.4825. How would you do that on your calculator? Well, second, natural log button, 3.4825, and I find that x is equal to 32.5410. Okay? I mean, it really is just like algebra in the sense that if I'm going to move it, I've got to take the inverse of it. Okay? What I'm looking for is that. That's my unknown that I'm trying to solve for. So I literally move it to the other side. Okay, now, if I had taken my calculator and gone e raised to the 3.4825 power, it gives me this. So you can do it either way. I can take this and I can write it in exponential form. Okay, and you're going, what? Y'all remember that? Going back and forth between it? So this is the base of e raised to this power is equal to that. Or just take the anti-natural log of it. All right, I want to show you, well, and I want to show you why that this was created. Okay, so if you look on page 622 at the top, it says the United States Post Office took 77 years to issue its first 600 stamps and 37 years to issue the next 600. Approximately half as long to issue the third 600 and so on. These figures suggest that the time needed to issue a fixed number of stamps has been decreasing exponentially. In fact, the number of stamps issued is growing exponentially and is approximately modeled by this formula. Do you see that that formula has an E in it? Okay, that's why we have to end up doing this natural logarithm with an E. Because if an E ended up in an exponent, I'd have to know how to get it down. So you're going to have formulas that have an E in them. In physics and economics, and so you have to understand that E has a value. The number E used in this exponential growth problem is used extensively in science and math. It is an irrational number whose value is approximately 2.718. E is the base for natural logarithms. Okay, so it's just a matter of, at one time you discovered what pi was equal to. Now today you're discovering what E is equal to. Typically, from this point on, they can't use the e as a variable in a problem. Okay. All right, look at example number 3. Okay, use the formula. Now this is the formula that was over on the other page for the post office thing. S is equal to, so that's the stamps are equal to 83 E raised to the 0.0224 times T power. Okay, in natural logs, to determine about how many different U.S. postage stamps will have been issued from 1848 to 2008. Now, that's going to be 160 years, okay, if you did the math there. So, literally, all I'm going to do is 83 times E raised to the 0.024 times 160 power. Okay? Now, I don't know why they did it the way that they did it, but, you know, you've got a calculator that you can put this into the calculator. They did natural logs of it, but I don't know why that would be the case. If you did 83 times, and then you did E raised to, and put that in parentheses, 0.024 times 160, and you're going to get a 3,861 power. Okay, which is exactly what the book did doing the anti-log. So I don't know why you would do it that way. You're literally just plugging it in, okay? If you look at what the book did, look at example 3, they took an anti-log of both sides, okay? So then they turned around and they literally did the log of 83 plus 3.84 times the natural log of E. I don't know why they broke it off like that. It makes no sense to me when you can just plug it in. Okay, move down to look at example number 4. Okay, example number 4. You have Mr. and Mrs. Franco are planning to take a cruise for their 25th wedding anniversary. They have 6 years to save $3,500 for the cruise. If the 6-year certificate of deposit they buy now pays 8% interest, compounded continuously, how much should they invest now in order to at least have $3,500 for the cruise? Okay, so they are going to use that PERT formula that we talked about. PERT is principal times E raised to the rate times time power. They have to have at least $3,500 to take this cruise. Okay, what we're trying to find is the P. Okay, I think that's what they, no, did they say the P? No, they say the 8%. You don't know the P, okay? You have P and you have E raised to the rate is 0.08 because it's 8%. And it's a 6-year certificate, so that is going to be times 6. Okay, you with me so far?
So the PERT thing, what is
It's a
this
formula. It's a formula to understand how much money you'll get if interest is compounded continuously. It's a business formula, okay? So literally I knew what the rate was. It was 0.08. I knew what the time was. That's a 6-year certificate. I know that I need to at least have 3,500. Let me reset this.
So the E is this natural